for 60 years did a number of technical things in support of the nuclear weapons program, all the way from making components that were used for explosives or radioisotope work, but also we had as a spin-off some space things. And there was a recent landing on Mars. You know, I'm not sure that we have one of our systems on there, but many of those came from here. All of that started in 1948 at the building of the T building, the underground building, and then we had many assignments since that. So what I want to talk to you about tonight is the weapons component testing and fusion research that we've done here at Mound over that 60-year period. So the outline is that we'll talk first about the development of the hydrogen bomb. And this is following World War II. And we'll talk about Mound's role in the nuclear component performance testing. All of those involved deuterium and tritium, which is a radioactive gas. And so we had to figure out ways to handle the tritium gas. We had to measure quantities of gas very accurately. And we needed to develop analytical tools that could measure the hydrogen isotopes and their composition and any impurities that would crop up. And then we were set for the cleanup at closure. Many of the same equipment was used to keep us safe as it was closed down. And finally, we'll end tonight talking about controlled fusion energy. Two different methods. One is the magnetic DT plasma confinement method, and the other one is laser fusion. Okay, nuclear fission and nuclear fusion, they both can release energy in a very short time, generating an explosion, and we typically call that a bomb. And so when you're talking about the atomic bomb, that was a fission device. The hydrogen bomb is a fission plus a fusion device. So let's look a little bit at the history of both here. Fission was first observed back in about 1938 by Hahn and Strassmann in a laboratory in Berlin, Germany. They couldn't figure out exactly what was going on, that the U-235 nucleus appeared and lighter mass components seemed to appear, and it wasn't alpha particles or beta particles. So what was it? Well, actually, Lisa Meitner explained that about 6 months later, but she had already escaped to Sweden at that time. But she did share that information with the free world as well as in Germany. Here in the United States, Glenn Seaborg discovered plutonium as an element in the isotope 239, which turns out to be fissionable also. So at this point, this leads up to the fact we have two fissionable materials, and we learn more about it by looking at the work of Enrico Fermi. 1942, he made Chicago pile number 1. And from that, he was able to generate an increasing power output from this pile by removing some of the control rods. So he learned how to control the reaction. And that is using the delayed neutrons of U-235. The Manhattan Project designed critical masses that the prompt neutrons would make it go off. Okay, so same process in fission for the atomic bomb and for a reactor. Fusion. What is this all about? Well, fusion happens on the sun as constantly. Even tonight it's going on. Generating enough energy that comes up to us as solar energy in the form of light and particles. Fusion was first demonstrated on Earth by an Australian, Mark Ellefson, in 1932, which is long before World War II. But he was at Cavendish Lab in England and was able to take some of the equipment from the first alpha particle scattering and actually do a fusion experiment and measure the result. After World War II, Oliphant encouraged Edward Teller at Lawrence Livermore and others too, that we ought to add to the output of our atomic bomb by being able to use fusion, deuterium-tritium fusion, to add a large amount of energy as this arms race began and carried on through the next few years. So a hydrogen bomb uses DT fusion to increase the power output of an atomic bomb. And the fusion things that are available is deuterium with itself or deuterium with tritium. And the one that is chosen is the deuterium with tritium because it's about 4 to 5 times as much output yield per event as you get from deuterium fusing together. So various prototypes after 1945, there were plans toward this, and the various designs were tested in 1951 and 52 of hydrogen bomb designs, and from the results of those tests, a particular design was chosen for making the first hydrogen bomb that went into the stockpile of weapons. So once you start having a, quote, product that needs to be made reliably, you need to have some kind of quality assurance function. So in 1955, Mound was contacted and assigned to do quality assurance measurements for the DT gas handling components, the gas delivery, the quantities, measuring these kinds of things. And with that came the requirement that Mound now had to deal with a new radioisotope, tritium. So our tritium operations began in 1955 and continued through 2004. So what is tritium? Tritium is the rarest and heaviest isotope of hydrogen. Ordinary hydrogen is a proton and an electron, the simplest chemical we have. If you add a neutron to the proton, you end up with twice the mass of it, but it still behaves like hydrogen. If you add another neutron, you get tritium. And the thing about that is it's still hydrogen, but it is very unstable. It turns out that one of the neutrons wants to become a proton, and eventually then with 2 protons you have helium-3. So the tritium beta decays, giving off an electron from the nucleus called a beta particle, plus helium-3, and it does that with a half-life of like 12.36 years. That value was also measured here at Mound. The energy of the beta is really very low, so it doesn't take much to physically shield you from the tritium radiation. What you want to do is to control the hydrogen so that it doesn't just go everywhere. So you have to handle the hydrogen in plumbing. The other thing is you don't want to ingest tritiated water to be part of your body pool of your body, because then the beta particle can do damage to the tissues of your body. So that's the biggest concern with tritium, is physical containment as well as not having it get into the bodies of workers. The fusion process actually generates energetic particles. D plus T gives helium-4 and a neutron. The neutron carries off most of the energy. This can be used to boost the power of a nuclear weapon. In the same DT reaction, we can consider for a future source of electrical power. And at the end of the talk, we'll get to discussions of tokamaks and laser fusion reactors. Tritium at Mound, there's a number of different areas where activities that we had to do in order to safely handle it and contain it. We had the task of doing the component evaluation, measuring gas contents and compositions, and the quantities that were delivered, and the timing at which they were delivered to the reaction vessel of the weapon. Okay. Basically, all of this to generate data to have someone say this would work or it wouldn't, because this is a way of measuring the quality of the stockpile. If the stockpile is credible and reliable, then it is a deterrent. Without that confidence and information, it no longer becomes the deterrent that we think it is. Okay, so other things we did was process development. Making new chemical forms of DT fusion fuel. We also did some actual gas loading and production capability. We had the ability to load gas bottles as a backup function. We had materials research on materials storing hydrogen, specifically tritium. How do you store it, and how do you do isotopic exchange with it? The tritium containment and recovery was an effort to minimize the release of anything to the environment. Bear in mind, at least half of us live downwind from the lab. So you don't want to follow your own nest by letting something go. And we'll see that there are serious efforts to doing that containment, not only the primary containment, but a secondary containment of the flow boxes. So we're going to talk next about component evaluation as a quality assurance program. This is a description of the connection of the whole Department of Energy nuclear weapons complex. There are design laboratories, some you've heard of, Los Alamos National Laboratory, Lawrence Livermore National Laboratory, and Sandia National Laboratory. They all get involved with the military in designing a weapon for future situations or upgrades of the ones that exist in the stockpile. Okay, so as they develop something new, they use Mound as a testing grounds for, how well does this particular design work. Then you have production that happens where you have people build things and they are built to some specification. And some of the questions are, by taking samples of their product build, one can, and analyzing it here, we can say they built it to the specifications or not. Then normally those products would go to Pantex in the Panhandle of Texas. And they would assemble the weapons into the actual nuclear device that gets put into storage or into a missile. So they would, if there was a new design, you would have new material laboratory tests, and they would do sampling of that and send it to Mound for performance tests, and likewise stockpile testing of older weapons that get disassembled and the components sent for how is this aging? In other words, after 10 years, would it still work? And those questions can be answered by looking at the data. So this is a description of what would happen with our flow of materials. We would receive the nuclear hardware at Mound. We do some pre-tests with calorimetry, radio counting, and x-rays, just to find out physically what is it we're going to be analyzing. And then we would do environmental tests to simulate the flight of this particular device or its release. So what is the vibration? What are the accelerations it experienced? What is the shock? What is the thermal conditioning that you might need as it goes up into space and down were it to be launched, or whatever the application for that particular device is. Then at that point we would do function tests. and we'll focus a bit on this because that's the very much the value added here of Mound. And a lot of post-function tests that are analytical functions, disassembly and metallurgy, what's the surface of the inside of a gas reservoir look like, and how has it been aging. All of that goes together in a report that is sent to the design agency as a report on that particular set of tests. So what do we receive? This is an example of a gas reservoir that we receive. In a nuclear weapon, a mixture of deuterium and tritium gas is stored at very high pressure in a stainless steel container. And when you get it and arrive, it feels warm. And this is because of the radiation from the tritium inside generates heat, releases heat, and it feels mildly warm in your gloved hands. You put on gloves, that's just good practice. Then this reservoir then is taken to calorimetry to measure that heat output very directly, because the heat output comes from the tritium. And from knowing the watts per gram that comes from tritium, you can actually measure the grams inside of this bottle with never opening it. And there's a demonstration calorimeter in the back. If you have some time at the end, you can see a design of a twin bridge calorimeter that did these kinds of measurements. Then after measuring by calorimetry, the gas transfer lines will be connected and it's ready for environmental testing. Let's go to the calorimetry again. The design of a calorimeter is a twin bridge design in a water bath so that you have two equivalent systems. You can put a sample on one side, and on the other side you can put a heater. And you can measure the temperatures of both sides. And when you have balanced the heat that you put in on one side to the heat generated by the sample, you then know that you have a very accurate measure of the watts that are being generated by the sample. Once you have the watts, you can go to the table of radioisotopes that we can measure by calorimetry and find tritium generates 0.323 watts per gram of tritium. So by dividing your measured watts, you can say how many grams of tritium is in this reservoir at the date that you actually measured it. Because this is a radioactive material, the radiation goes away with time, and so you can actually calculate the value of tritium at some future date, or the date that you do the measurement. Okay, then the components that are received are exposed to environmental testing, simulating G-forces and vibrations. By putting it onto a shake table, the G-forces are programmed and applied for some period of time. And then with this shake, rattle, and roll simulation, this is a simulation of what this particular device would experience in a delivery flight. Okay, similarly, the components are exposed to a thermal history by putting them in a heated chamber for some duration with a prescribed heat ramp for it. Okay, at this point then the components are ready to be assembled for a gas delivery test. Okay, the gas delivery system, this is a typical setup for it. This is this little round reservoir that we received and we measured by calorimetry how much tritium is in there. But at this point, we take all of the plumbing that would be with the device, and it's the actual plumbing that would deliver the gas to a war reserve volume. This volume, we simulate what the volume is so that we can simulate the back pressure as the gas goes through. It's pushing against back pressure, and that changes the delivery time and the flow rates. So we need to simulate that very carefully. notice that all of this is inside of a little red box here, which is a stainless steel bell jar. And that is, if any of these components during the test were to leak, we want to be able to capture all the gas inside of this bell jar, and we can remove it. Another thing is we can laser drill. If this explosive valve that starts the timing sequence doesn't function, you can laser drill and relieve the pressure so you don't end up with, what do we do with this? Yes?
Now, are these tests on samples that have served on duty and you're looking after their duty life is essentially over, or is it before delivery to manufacturing?
It is delivery from manufacturing or disassembly from the stockpile. It is without any of the explosive components. It's gas only. And so what you're looking at is, are the right amounts of gas there? Is the flow rates and delivery quantity and time in the right amount of time? In other words, we gather that data, and then from that, you can judge that, yes, this would have worked as designed. And that's it. So, yeah, this has not been functioned or anything before. It's sitting in the stockpile as part of our deterrent. We frankly are not interested in using them, but they are there as the deterrent. Okay, so the sequence of this, we'll lower the bell jar, and then actually everything else is inside a secondary containment. The blue line is the glove box, and all the work is done to assemble it through gloves. We have some fast dynamic pressure and temperature gauges, and again, duplicates of them, because you only get to look at the data once. So you want to make sure you've got good data. So there's no excuse for not having good data. So we would gather the pressure measurement data from 2 devices, and likewise with the dynamic temperature. They're just a fast response. Then later, after this is settled down, and it will develop a better pressure measurement from static temperature and pressure measurement devices. Then when all of the test is done, the gases are put into tanks, and they are analyzed for quantity and gas analysis. So what's the timing of this? The war reserve valve that is actually on the item itself starts the event and starts to deliver the gas at a prescribed time, which is the expected detonation time for this spec weapon. You would do a cut, seal, and divert for the gas. What that does is seals off the gas that was delivered. It diverts anything from the rest of the bottle into an empty tank, and so we can do a quantitation of all the gas that gets transferred, plus the gas that remains, and all of that information can be blended together so that we can compare with the fill data decayed to the date of the test. Yes?
The cut, seal, divert valve, is that something that Mound would have had to design and develop, or does that come from the weapons designers?
I believe it's a Mound design, Jack?
The actual valves were usually designed by the lab, but we made components for them, as in the explosive charge.
Yeah, but like certainly the detonator explosive charges were made here, and that's a different story. Okay, so all of the gas fractions then are captured and are put into tanks. A little bit about what does it look like. Whoops. I know what you're having problems with, Sue. This is the bell jar, and it extends up over and into a dome over the, but it's still inside the glove box there. So you can assemble everything on a plate and lock everything down, doing that through gloves that are accessible from both sides of this glove box. And then when you have everything connected and all the electrical cables and that, you can lower the bell jar. So that would capture any kinds of leaks once you start function testing. Any leaks that go beyond that would be caught by the glove box, so that you have a second containment to transfer this. Now this can be a fair amount of gas, fair amount of tritium, so you do want to have redundancies into this so that it doesn't go up the stack and you follow the nest or something. Okay, so that, this is the outside of that glove box, and then the electronics panels that were designed and built here to do these tests. The gas then is transferred to a low pressure tank for more accurate measurement of gas quantity and composition. The actual quantity delivered to the simulated bit of this device is actually at elevated pressures, high enough that there is in the calculation of moles of gas quantity, you'd have to worry about the compressibility factor. And that compressibility says that if you put more gas in one space and raise the pressure, not all the molecules have the full volume to occupy. They run into other molecules. And so as a result, you can effectively say that the volume divided by Z is a way of reducing the effective volume that you can actually occupy with a given molecule. So by going down to a low pressure like near atmosphere, the gas constant is about 1.001. It's basically within a 10% of being an ideal gas. Okay, so then what do you do with that data? Once you have the moles of gas, you can multiply that by the mole fraction of tritium that we'll measure in a minute, times 6.032 grams per mole. And once you have that, you have a number for the grams of tritium in this particular tank. Now that could be what was delivered. There can be other tanks that you have to add in order to finally compare with the fill number decayed to the date of the test. So, another interesting feature of tritium is we put it into these, in order to get the pressure down to around atmosphere, the tanks were something like this, maybe about this tall from the floor. So that's a pretty good sized tank, and in the middle there's a chance, even at an atmospheric pressure, for the tritium heating to start convection currents. And so we always would put in at least 2, maybe more, temperature probes at different depths into the, and so you can actually make some kind of a model or profile of what is the average temperature for the gas, because that average temperature goes into the calculation of the moles that we have. So, and so how much change would there be at an atmosphere in a particular case? Maybe like a ½ degree centigrade. Measurable, but not huge, but it's worth correcting. So we would do that. So then the final thing that we do is we've measured the moles and calculated that from this data. Now we need to find out what's the mole fraction of deuterium, tritium, and other materials in the gas composition that was delivered. So we need to take a sample. So this is actually a little micro-plumbing system, a capillary, which draws the sample to an analytical lab. And once we get it to the lab, we can analyze it by mass spectrometry and do it. I'm going to send around, this is an example of a capillary. It's not the one we used at Mound. The ones we used at Mound were twice as thick because they were rated for 50,000 psi so that you could run them, through conduit and things like that. But this one, the same principle is good for sampling. We use it every day, and it is a small capillary. You can look at how small the inside diameter is comparatively. The wire on the right is a wire that's the size of the capillaries used for like a 150-foot length. So I'll let you just pass that around and take a look. Okay, so from this volume you would go to a particular site. All of that is documented as someone calls up and says, I want capillary number 76A run from my tank. And so you go and open that up and draw some sample, flush the old gas that's in it, and gather a sample that represents it. Typically we would take 3 samplings of it so that you could look for agreement that is just normal statistics of the system. That's one of the best ways of assuring that the gas that you have measured is the same gas, and then all you have to worry about is the accuracy of the composition. And we'll get to that in a minute. This is another glove box, here with the gloves on, but with the gloves off, you can see these tall trees here that have a number of valves on them. Each valve goes to a capillary to some place in the process. Now in the INFICON building we had 2 laboratories, and there were 2 sets of capillaries from every volume. One that would go to one lab and one would go to another lab, so if one lab was busy you could get the analysis from the other lab. Or you may prefer your analysis from one lab or another. But this allowed for good trace. Okay, so how do we analyze it? Well, over the years, when I arrived in '72, we had mass spectrometers that had been used probably since 1955. And the thing about them is they're very stable, they're very good for what they can do. And so those were the 2 principal cycloid mass spectrometers, one set up to look at the hydrogen isotopes, and a second one to look at the impurities and to do stable isotope measurements for other programs. But basically it's a fixed magnet, a permanent magnet, that establishes a field from north to south, and there's a pipe that brings gas into a region where an electron beam ionizes the gas. The gas gets accelerated and mass separated so that you can find a particular accelerating voltage that a particular mass will exit, and you can measure its intensity. And so that's basically how you do it. You scan over these masses, and then you take the chart paper and digitize it, take it to the big IBM computer in the sky and get the analysis, and the next morning you'd have your data analyzed. So in 1970, impatience arrived. The other thing that happened was we had an increased sample load, and we had the availability of computer control from some of the people on staff that knew how to use computers and make things work. So in this new lab that we established, we put all of the capillary sampling system into a glove box. Previously it had been in a fume hood. We had remote control of the capillary. This young lady could choose any capillary that was requested, purge it, get a sample, do the gas analysis, and in a matter of about 30 to 40 minutes could actually turn out a compositional analysis on a piece of paper. Didn't have to wait until the next morning. So this was a real improvement for the turnaround time, and it's especially true if you had to hold gas overnight and resample it because of something being wrong. Okay, we had some other alternative analytical methods that we have developed for measuring, independently measuring the helium and total tritium by something other than mass spectrometry. It's just good analytical practices to have multiple methods. One of them is we would take a sample into a volume, measure its total pressure, do a volume expansion into a titanium sublimation pump, which would gather all of the active gases and basically leave helium-3 and any helium-4 argon if that was present. Then if we wanted to, you could analyze the gas that's left over. If you're pretty sure it's just helium-3, then you could compute what is the composition of helium-3 in the system. While you're doing that, the same gas is exposed to a beta scintillation detector that we developed here. Here is a calcium fluoride crystal doped with europium to make it scintillate whenever a beta hits it. And the beta loses its energy in the calcium fluoride crystal. The crystal gives off light proportional to the number of betas that struck it, which is proportional to the partial pressure of tritium. So you have a gauge. And the only thing is you got to operate this in a range where the beta going through the gas doesn't lose more energy in the gas than it does in the crystal. So there's some requirements that we learned and use. The other thing is you can have very precise measurements of something, but what you really need for this application is accuracy, which means you can actually take something and duplicate the composition that it was blended to. So we needed to have deuterium, tritium, and helium gas mixtures. Well, they're not available. We went to NBS and they said, no, I don't think so. So they worked with us and we made them at Mound with an independent group doing the measurements of quantities and blending them together. From that, we had then known mixtures that could be analyzed. So the protocol was the daily routine for operators was to run the analysis of one of these mixtures. And if everything checked out that it's within the normal bounds, in other words, it appeared here within about a 1% accuracy limit, then we say, okay, things are stable, things are good, like yesterday, go ahead and do your test, which was always, I'm not sure I recall even the time we had to say no, but anyway. So if a mass spec was out of control, then we would do a rerun to note some permanent shift that had occurred. That could happen literally from power failures and other things like that. So this served a purpose for us, for our management. If there was a power failure, we would definitely make sure that everything came back to the normal status quo for analysis. So what do the mass spec do? Well, the cycloids are over here on the left. And for hydrogen, or for helium-3 and Hd, which are both nominally mass 3, there is about 1 part in 500 difference between the mass of each of those. So in order to measure them independently and use their peak height to represent how much abundance to be found, you have to do some looking at the peak shapes and things like that. So the mass spec leaders from DOE sites all over, there were like 6 different sites that needed a mass spectrometer that had the abilities to do better resolution of things. So we all got together and defined some specifications for a mass spec to be built that would meet our individual needs. We had a result of one company from the UK and one from Germany eventually became the suppliers for these, and they still are the suppliers to this, this community. The solution to it is to use a magnetic sector, a higher resolving power, and we'll see one in a minute. This allows direct measurement of the ion species. Notice these where they are unresolved now are 2 separate peaks. You can drive a truck between them. And if you're looking at helium-4, it differs from deuterium by 1 part in 180, and it's miles apart here. So you can do direct measurements of all the hydrogen isotopic combinations for the molecules, besides measuring helium independently. So what do they look like? This is an example of one of the magnetic sector instruments, a 30-centimeter radius. Basically, this cabinet is about 7 feet tall. So they're big. You need a fair amount of space and floor space. So we actually built a new laboratory for a new project that was coming along in T building. And we had 2 of these mass spectrometers. Again, it's a matter of redundancy so that at least one of them was working. Then the control of this, like most things, was done by a computer. We had a computer for each separate mass spectrometer and a separate sampling system for each of them. So we could have one operator operating 2 mass spectrometers and getting the sample throughput that was demanded. Typically, someone called and requests a sample analysis. They would have an answer in hand by 20 to 30 minutes later. I'm going to shift gears now to another function at Mound, which is process development. And with this are the developments of special compounds or new designs of things to work with the design agencies. And this is an example that goes back to Operation Plowshare. This is back in the late 50s, early 60s. The idea was these nuclear weapons can make nice big holes. We ought to be able to make a new harbor or maybe a cut through the Rockies or something for a new road. But this should work, so let's see what we can do about it. So here at Mound, we developed a solid version of deuterium tritium by chemically reacting it with lithium. And so that became the, instead of a gas reservoir, it was a reservoir of lithium deuterotriti. So these materials are fabricated and pressed here, and they were shipped to Nevada for assembly and this test. The result is this sedan crater. It's 320 feet deep, about 1,300 feet wide. If you want to see a picture of the excavation process, it's downstairs in the museum and runs regularly. Other basic research on materials were conducted on many tritium compounds, like metal hydrides especially. The reason that we would do this is we needed the information for our own research, but we would publish information and that because we had all of these analytical tools available to us for doing good fundamental measurements of things. And some of the, we talked to, this is Bob Bowman. You saw him earlier. Here, there he is. Yeah, half of Bob Bowman. We all changed a little bit. But Bob can tell you more of the details of it, but suffice it to say some surprising things. As the tritium decays and becomes helium, the helium blows bubbles inside the metal materials. And eventually it'll make its way out, but it still retains a certain amount of it. And a lot of this data that was generated is now pertinent to the work that Bob does at Oak Ridge on hydrogen storage using metal hydrides. This is an interesting one. I think a measure of Mound's advanced tritium processing was our recycle of tritium waste and our tritium enrichment methods. One would, if you had the exhaust, if you wanted to get rid of tritium, you would just take it to a pump, and the pump's exhaust would go to what was called the effluent removal system. And it would take the hydrogen gas and convert it into water, and then you could eventually take that water and mix it with concrete and bury it as a block of concrete out in the Nevada desert or some appropriate place. And there goes the tritium with it. So this design is water that comes out of here, we have a feed water cleanup system so that you can put it into a distillation process that it would use electrical distillation to make hydrogen, and that hydrogen then could be enriched cryogenically and finally polished up to 4/9 pure tritium. This was a system that was here. So why would you do all of this expense? Why not just bury it? Well, I think the answer is you need to figure out, can you do this? But things like scrap, LIDT, and UT3, some of it was shipped to Mound from off-site, either off-site water or recycled materials. We would take the tritium gas off from it and enrich it back to a high-purity tritium. Tritium is valuable, $30,000 per gram to make it in a reactor, which is like $3 per curie of it, and in your little tritium watch you might have $30 worth of tritium in it. Okay, but the savings is by recycling this and getting the tritium back into the DOE cycle, you avoid making it in a breeder reactor. And so that's a cost savings that can offset the cost of doing this. Okay, along this line, as we got close to shutting this place down and cleaning it up, you're going to have some off-gassing of tritium from things as you take it apart. So how do you capture that? And the answer is, just like we had before, with an effluent removal system, but this new facility was added in 1998. This is after the decision to close down. But to provide the capacity to be able to sample air as you're doing a disassembly process and capture any tritium that might be there. So that was there, and probably the last thing to actually be disassembled as all of the other materials left. This is a mound safely handles large quantities of tritium. Okay, early in the tritium operations, starting back here in the early 60s, they started to keep track. They figured out a way to measure what is the tritium going up the stack. And this is an amount of curies per year that would go out. Notice that there's a dramatic decline that occurs along about 1968. And that was the decision point to say, we got to have something other than fume hoods to send this and protect the people. The people were protected by the fume hood, but it would go out into the atmosphere, and you know, it's not a good thing. I mean, it was not seriously bad. However, it is something we just should not be doing. So we put things into glove boxes. The decision point is here that any new process was going to go into a glove box so that you had a secondary way of capturing the tritium so that it didn't go out. There's nothing better than data to say, are you effective in doing that? You can watch as the time goes on and more of these things end up being in glove boxes. The emissions out the stack go nearly to zero. In fact, at the end of it, we were doing like 1/500% of the total inventory was going up the stack at any given time. And we had some significant quantities of tritium here. Okay. Mound's involvement with the energy program. This is too interesting not to continue. At least to me. Important example of nuclear fusion is the sun itself. If you look at what we know about the sun, some interesting things. We see the outer limb of the sun, and we say that daylight is basically 6,000 degree Kelvin surface of the sun emitting black body radiation light. And that's what we see. In fact, if you go to the store and you buy a daylight white light, it'll have in little numbers underneath 6,000 Kelvin. If you have a soft white, it's maybe like 4,100 or something like that. But this relates to the surface temperature that we see of this emitted light from the sun. Inside the sun, there is such a mass of material that the sun inside has a much higher density of hydrogen, about 150 times the density of water, and it has temperatures high enough that the hydrogen fuses into helium. Now inside here, because of the very high density, you can fuse hydrogen at about 16 million degrees Kelvin. When we do experiments here, we can't produce densities like this. So as we do experiments on Earth here, we have to raise the temperature in order to have fusion occur. So how do we do that? DOE's approach is twofold. They have two different kinds of fusion activities. One is the magnetic confinement Tokamak design, and this is just a large torus, basically a donut, and on the inside of the donut is a hollow volume where low pressure gas resides. This is almost to the point of being able to stand up in it. Some of the later versions, a person can stand up inside this, obviously when it's not running. But this is sort of a standard man for an example here. The other design is the other design is inertial confinement laser fusion. Wow. And the laser fusion is done at two different places. One is up in Rochester, New York, the Omega system. The lasers there do direct drive. We'll look at that. And then there's an inertial confinement system at Lawrence Livermore in California, the National Ignition Facility. So how does the Tokamak work? Basically inside this torus, the donut area, that is red is the DT plasma, D plus and T plus ions and electrons at a very low pressure inside the torus. And it's kept away from the walls so it doesn't melt the walls by a combination of coils producing magnetic fields. Those magnetic fields will steer it into a small confined beam. That same magnetic field can be used to compress the plasma to increase its density, and you can add energy by putting in deuterium, beam of deuterium ions. And the key is that you get a high enough temperature that you can actually fuse the deuterium and tritium together and produce a helium and neutrons. In this reaction from the fusion, there is a neutron produced. That neutron can run into a lithium blanket on the inside of the device, and in the process generate tritium plus helium. That tritium can be later harvested as the next generation tritium. So you breathe your own tritium as you go. The design of this is intended to be for a power reactor at some time in the future. Mound provided tritium technology for the operation of one of the early Tokamaks, which is Tokamak Fusion Test Reactor at Princeton Plasma Physics Lab. We provided assistance for the tritium handling aspects. We provided hardware like uranium bits for storage of tritium, primary containment, design recommendations, glove box, tritium effluent management, consulting work. But I think the key thing was we had their engineers and technicians come to Mound, work with people that deal with this every day, so that they ended up with learning the culture that we had here and could transplant it to another metropolitan area, namely Princeton in New Jersey. So the tritium training course was also given at Mound. We would take that and give it to all the Princeton employees also, so that everybody had some idea, what do you worry about? We had instrumentation that was provided. These bubblers and other standard devices that have worked well for us here, our beta scintillation detectors. We even worked with them on their quadrupole mass spectrometers of how to get a better measurement. So what happened to TFTR? Well, it's still there, but its real claim to fame is that they achieved the first controlled DT fusion of 3 megawatts. This is not chump change. 3 megawatts within the TFTR on December the 9th, 1993. Then they did other kinds of experimentation. I mean, basically, it's a research facility and this kind of thing. So that was but it became the precursor for the ITER demonstration reactor in France. So what's ITER? Well, the future of magnetic confinement fusion was probably going to speak French. ITER is the largest tokamak made to date in the central eastern part of France at a town called Cadarache. It's designed to produce 10 times the power out to the power in. So in other words, in order to confine the plasma and have fusion occur, it takes 50 megawatts of input, but you get 500 megawatts output per all the fusion reactions that ultimately gets converted into thermal energy. The duration of how long does it work, it's not seconds or anything, it's like 1,000 seconds. So that's a reasonable period of time to generate a burst of energy that you could use to run a turbine or something like that. Then 500 seconds later, you can do it again. So this is an engineering reactor designed to make electrical power for the 2040s. It's always 20 years ahead. But we've seen this since the mid-70s. But basically, it's an interesting thing. It's a joint effort of 35 nations. Worldwide, there's 220 tokamaks of various sizes and designs that have been built. 50 of them are still running, primarily as training devices for students and engineering developments and things like that. The schedule for ITER is by 2025, it will be built. Currently, it's about half done. You can see some pictures here. I mean, these are real pictures. There's hardware. 5 stories high and about the equivalent diameter for the device, and a lot of support facilities. So plasma operation, first plasma by 2030 with deuterium, so there's less contamination. Deuterium tritium plasma in 2035, and then we'll have operational results for design of future engineering reactors or reactors themselves. Okay. We're getting down to the end. There's 2 inertial confinement laser labs in the country. One is the University of Rochester Laboratory for Laser Energetics. If you know anything about Rochester, this is Eastman Kodak. These are the people that understand optics. And so they built the first direct energy laser fusion system. Lawrence Livermore has a system that is, this is about 1 football field, and this is about 2 football fields long and 1 wide. Huge facility. We'll see what the size of the target here is in just a second. Okay, but let's look at how does this work. Laser fusion uses either laser beams directly to ablate off the surface of a contained quantity of DT fuel, and all of this happens very fast, so the fuel doesn't leak out. You basically first vaporize the outer shell. The inward plasma compresses the DT fuel. It reaches about 20 times the density of lead and about 100 million degrees for fusion. And thermonuclear burn spreads through the DT plasma, giving more energy out than it puts in. That's the goal of the NIF laser. Here, we don't get anywhere near that goal with just the omega laser. But this is, you need to crawl before you can walk type of experiment. So what did we do at Mound for laser fusion? Well, we loaded the microspheres that were used at the University of Rochester lab for laser energetics. Here's an example of, you can see the eye is pretty well in focus because this little sphere of like a millimeter or less is very close to the eye. That's the target that we fill with deuterium gas. Now you don't go to the station and grab the hose and fill it. We loaded them here, and we'll show you in a second how we did it. So basically that was done for University of Rochester. For Lawrence Livermore, we did some palladium hydrate storage beds, just some facilities for them to be able to start up their tritium handling, and then a beta scintillation detector so that they could measure the compositions of things. Okay, so we first filled glass microspheres, which are like 1/4 of a millimeter in diameter, and the wall thickness is about 1% of the diameter. So it's very, very, very small and thin-walled, but it's spherical. The other one is a larger 0.8 of a millimeter. It's huge. It's almost a millimeter. And it is a plastic microsphere that has been coated with different layers of things, but it's still basically plastic, polystyrene. And over here, this shows how you fill one of these plastic ones. You can do it at basically room temperature. This is the temperature plot on the right side. The pressures that we would step them up and wait for the gas to diffuse through the wall and fill the inside. Then you could increment to a higher pressure on the outside without collapsing the ping pong ball that you were trying to fill. I mean, a ping pong ball is a good analogy of the relative size and thickness of these shells. So then the thing is, we would very quickly drop the pressure. Note this is about 1200 psi, so it's like 80 atmospheres or something like that. We would drop the pressure and then immediately would put this into a dry ice bath and ship it to Rochester overnight. For the glass microspheres, they were loaded with DT gas by a high temperature diffusion of hydrogen through the glass wall with pressure steps. And here we go through the steps. The temperature of this would go up to about 360 degrees centigrade. And then the diffusion rate of hydrogen through the wall is substantial. So you could add these in stepwise and get all the way up to something like 400 atmospheres. Why that high? Well, because you're going to cool it down. So after we get it to that height, then we start stepping down the temperature of the glass and lowering the pressure. So by the time we get down to room temperature, or actually eventually put it on dry ice, it goes down to 200 atmosphere at room temperature and down to 145 atmospheres on dry ice. So why is that important? Because we would take that unit, which is all the microballoons are inside this little egg crate that we got from them. And the crate was put into a primary stainless steel shipping container and then taken outside the glove box and put into a secondary one, surveyed put on dry ice, shipped to the airport for the next day, and then they would mount it using spider webs as the way to support it, and then get it in the center of their laser spheres and get everything focused. They could use their mirrors and actually see the target, and then hit the lasers, and bang, you would have some fusion events occur measured by neutrons appearing. And that's the classic way of making sure you've made a fusion event. Okay, the last one is the Lawrence Livermore National Ignition Facility, the indirect drive laser fusion. Here you have this bank of lasers, and they all have front surface mirrors, and they all focus on this little target hole round. Basically, that is a gold cylinder, hollow on the inside. The beams come in the ends and hit the walls, heat the walls, and to a temperature that is hot enough to actually make X-rays. And it's the X-rays that come off the walls that compress this 2 millimeter diameter target, and the DT ice that is on the inside of it. You compress that, and then you have a fusion event. And they have had significant fusion events. The goal of this is to have more fusion energy released than it took to make the shot. That has not occurred yet. This is just mind-boggling. The NIF target is 2 millimeter sphere in diameter, backed by 2 football fields of lasers that are focused on the entrance to this little hole round, so it can generate enough energy that this DT ice at 18 degrees Kelvin can be fused together. So how do you hold that target? And the answer is you have a very long probe, sort of like a pointer, and it goes out, and if you look at this, is about 45 feet, the whole length of that device. It extends something like 15 feet into the center of the sphere. And if we look at this section, this is where it keeps the gas cool, so it stays as deuterium tritium ice. Then if you look at this end here, that's the thing that holds this small target and hole round and that. So just having the thing out there wiggling, how do you hit that? And the answer is you can watch it and time it so that you do the beams when you know where the position of it actually is. So that's pretty much it. I'm going to summarize this, and then we're going to hear a bit from Ken Phipps here. Mound supported nuclear weapons programs and space programs for over 50 years. We provided high-quality data and creative input to the many DOE programs. We were real partners with the design agencies, we safely transferred all radioactive materials to other receiver sites. We provided them with the training on how to accept the technologies that we did so they could do them. They are still going on. We decommissioned buildings and literally decontaminated the ground, and now it's a successful industrial park, as Sue mentioned earlier. We invite you all to come back to hear more about Mound Technologies as they're presented downstairs and in future talks that we will have here. So I thank you for listening all this time.